Yeah, here it is. Let me just think this is that's good now. Yeah, it looks good. Looks a bit blurred though, but all right. It's cool. All right. There you go, guys. All right. So, all right, AC current. This is what AC current is. And so that what it is. All right. All right, we're explaining why. Anybody remember why we said the current reverse the flow from last class? I did mention it, you know. All right. Does anybody know the source of AC current? I'm going to stare the whole night. Okay. AC voltage is that's that's you know that's um what's that, Giovanni?
Like magnetism in generators.
Oh, well, and you're saying the same thing as what Gennari is this texting. Yeah, it has to do with magnetism. So that's it. It's magnetism is the source. Let me so I don't understand why does it want to know that magnetism? Um
Yes, sir. I remember you saying something about copper also, like copper and those things.
I said something about copper. Oh, see, I did. Okay. All right. AC current, guys, produced from magnets. The device used to create AC current is a generator. All right. So Giovanni said AC voltage. Well, yeah, it's actually voltage first, then the current. So, but then before even the voltage can be there, you need the magnets. All right. So um usually this is a common question I'm asking in the CXC. Um, and this diagram here is familiar, quite familiar to anybody looking through past papers here. You're actually seeing you're seeing the basic components of a generator that is used to produce AC current. All right, we're seeing the magnet. And for some reason they switch the poles in terms of the color code. And usually the north pole is red and the south pole is blue, but I don't know. This person is trying to break tradition, but whatever this is saying, it is telling you that what you need two poles, a north and a south pole of a magnet, and of course, this seemed to be a wire. It's actually a piece of wire, and it's actually a loop of wire. So based on the shape, hold on a second. I'm trying to see if I can get a model here, but then it's Java, so it's not gonna open here. That's a some Asia blue. I need yeah, I need something in HTML. All right. This is not opening at all. No. All right. So all right. So no model tonight. But all right. So we have to work with this then. All right. So we have our magnets, and we have a wire, but then the wire is placed between the two poles of the magnets. All right. So the wire is going to be exposed to the magnetism. However, at the end of the wire, they have these rings on it. Now, the rings basically something to hold it in place. So it's coming like some screw thing where it allows it to rotate. So as you notice, these arrows are showing that there's a rotation. Everybody seeing these orange arrows here?
Yes, sir.
All right. So it is saying that it is rotating. It's rotating this way, and it's going 360 degrees. All right, it's rotating 360 degrees between the poles of the magnet. And so when it does that, it's still going to experience the magnetism, but when it turns halfway, it's going to, well, like, so for example, now, what you see facing the blue side, if that were to turn upside down now, which it will at some point, then it will be facing the south pole. So basically, with this system here, guys, the rotation of a coil of wire in the magnetic field is such that for half of the turns, they'll be facing the north pole, and for the other half, they'll be facing the south pole. All right. So that's like, for example, like the earth, for example. At the moment, is it sunny outside?
No,
If it's sunny, yes, sir.
It's sunny outside now?
Yes,
Where you're in where are you?
I'm in Florida right now, so.
That's nice. But Florida is 1 hour ahead. 1 hour ahead.
Not really sunny, but sorry, the sun is going on right now.
The sun
But
is
it's
here.
not night. It's not
All right.
night.
But okay, and because that has to do with the latitude. All right. The point I'm trying to get to now, guys, is this. All right. We don't have 24 hours of sun. All right. As a matter of fact, it's usually half of the time is sun, half of the time is dark. And it's because what? Rotation. Sun is always there, but it's not always sunny. Where I am at now, it's night, but the sun is still there. But it's just not facing where I am now. All right. So it's the same thing with the north and the south pole. Yeah. So half of the time it's a north pole, half of the time it's a south pole with the wire rotating. And then what that does now, if you notice the arrows now, notice that on the blue side, the arrow is going up. It's going this way. So arrow is going this way, facing the north pole. But then when you're facing the south pole, the arrow goes the other way. So that's the concept with alternating current. That is why it changed direction, guys. It changed direction because it is facing a different pole in the magnetic field. Any questions there?
No, sir.
Right. So we could look at it in many different ways. In real life, it could be the difference between your mother and your father. Your father allows certain things, and your mother allow the opposite of what your father allow, and it's a thing, So, and that causes you to act in a certain way, and that's what happens here. because the electrons in the material, in the coil of wire, all right, this loop of wire, it is causing it now to actually move up this direction and down this direction. And then now it's gonna reach eventually what we call the rings. And what they have here, slip rings, them call it. Slip rings prevent the slipping. So they call it slip ring, prevent the slipping of the loop. All right. And then now they have some contacts here which connect it to some other wire. And this wire now is what we will connect to. This, they are actually called brushes here. So again, this is a common question in CXC. They love ask about slip ring. In fact, it come on both paper 1 and paper 2. All right. So slip rings are used. All right, because why they use they specify slip ring here is that the slip ring allows this to rotate 360 degrees. All right, so are used in AC. All right, so are used in AC to promote. And then guess what? There's DC generator as well, but then we'll talk about that some some other time when we see a question on it. But are used in AC generators too. Rotation of the coil of wire. I can say loop. So that means that, well, if you guys were to walk between two big magnets, you guys, things could happen to you guys. You guys could become electrified. You guys could start conducting electricity. But then the catch is that there are no magnets that powerful for that to happen. All right. The strongest magnet you're going to find in real life is when you go to MRI. But ever hear about MRI yet?
Yes, sir.
Yes, sir.
All right. What is an MRI? What do you understand from it?
I think it's a scan, sir.
It's a scan. But it's more than just a scan. The scan is the last thing that it do. So amazing though. How things get named after the last thing with them do. Or the least important thing with them do. You know? everybody remember the man who scored the goal, but don't remember how the man who scored the goal get the ball. But it's the same thing. The scan is the last thing that the MRI does. What does MRI stand for? The M in the MRI stands for what?
Is it magnet?
Yeah. Magnet. No, so the first word, so the first M, or the first word in the equipment or in the scan that you do is magnetic. All right. So when you go to the scan now, it's a big, strong magnet then put over you. So basically, it magnetizes parts of your brain. Your brain has electrons in it actually. So they use a very strong magnet, which is powered by electricity. All right. So yes, you're gonna learn that magnetism produces electricity, but the opposite can happen. Electricity can also produce magnetism. So that is the focus of class this evening, to see that the two of them are related and to see how you could be asked questions about that. But there's a big magnet that they use to see what is going on inside of you in the MRI. Very strong magnet. It's the strength of the magnet is such that it don't really harm you. So that's why it's better than an X-ray. Better than they have a scan named PET scan as well, and I think they have CT scan. So but the MRI have the advantage of just using magnetism, which is easier, softer on your body. And it just basically what they do now, the electrons there. In fact, you have some hydrogen there. Your body is 90, well, your body is 70% water. So basically that's what it does. The magnetism magnetizes the water. And by the way, water is actually magnetic. I don't know why they didn't teach people that from long time, like from basic school, but water is magnetic. So if it's pure, it's magnetic. So the MRI now is good there because it can magnetize, strong enough to magnetize the water molecules, and then it gives an image of where the fluid is. So that's how you can get a proper scan of the brain with an MRI, right? So magnetism is very powerful. Everything, guys, and get this in your head. Them tell you say only iron and certain things, man. Everything can be magnetic. You just need the right amount of magnetic force. All right, and that is something that you can actually turn things into a magnet using electricity. These are little tricks that you would need to know as a physics student. So, and even right now, facing magnetism today, the cell phone signals are actually magnetic as well. So it's getting there where magnetism will become more important in our life. But then just understand the concept here. All right, North and South Pole, as we say, have different pull. And any material that is in the field is the area between the North and South Pole where you can feel the force. All right, so that is a magnetic field. All right, so now rotating means say you're exposed to both North and South Pole, and then the motion of both, the force caused by both poles are different, so that's why the direction reverse periodically. All right. By the way, what we mean by a period is an entire cycle. So so yeah, it's actually half a cycle here. So this is 180 degrees, and down here, so it's 180 degrees, and the full cycle is actually 360. So what happens now is that if they were to plot it on a graph, and this is why I was actually showing you this last class, half of the turn is 180. When they plot the graph, that's what them give. This is the first half. All right, remember that this is usually time. So as time is going by, halfway through the turn, it is positive. And remember the axis them is like that. This is actually the current. Of course, you can have plus and minus current or voltage. Can call it voltage or current, doesn't matter. Same behavior anyway. All right. So for half of the cycle, or for half of the time, you would say that it is positive. But then for the other half now, when it facing the South Pole, it is negative. All right. Everybody see that? All right.
Yes, sir.
Yes, sir.
All right. AC. So this is the AC current graph. And AC current graph. All right. So yeah, so positive and negative, North and South Pole facing. That's what causes it. The slip rings, as you say, it allow that 360-degree rotation using generators to allow rotation of the coil of wire in a magnetic field. That would be the rest of it. In a magnetic field, which runs from North to South Pole. So it's the direction of the magnetic field is from the North Pole to the South Pole. All right, so that's it, North to South Pole. All right, and then that's pretty much it. Now, when you put so anytime you want to get some of that current that is being produced now, you just connect some wires and the brushes, and that's current for everybody. This actually is going to be AC current. And there is a symbol that they use in circuits for it. It's this. This is the symbol for AC current source. All right, a circle with a little wave there. To remind you guys that the AC current produces a wave graph. And why it produces a wave graph is that again, the half of the wave is positive and the other half of the wave is negative. That's why it's a wave graph. All right. And it occurs at different times. So you notice that, all right. So this is like 1 second. Let's call this 1 second. Time measure in seconds. So in 1 second now, all right. So I would say something like this would be half a second. So in half a second, the current is positive. The next half a second, the current negative. All right. That's pretty much it. It's still the same amount of current, because we have a thing with AC current called peak current. So it's gonna be the same positive and negative, but it's just that the force will be different. It's the source, you could say the source of that current will change because of where it is in the field. So that's how you understand AC current, guys. The graph is just there to remind you how it is being produced. It coming like if you go to the doctor. No, you go to the hospital, something really wrong with you, and them string up all kind of things on you, and them connect you, and them checking your pulse and everything. Right? You see the machine come up with some waves come up. All right. So they're hoping that it doesn't flatline. So for those of you who watch all them show, they like Grey's Anatomy and so on, them doctor show or ER and them show patient ever in a problem, they use that device there to see what's happening with the patient heart rate. So it's the same thing. So imagine this same graph is measuring the rate at which the current is produced. So if you were to work at a JPS, for example, that's one of the things that some of the engineers look at. They look at the wave, the graphs, because some devices, there are devices that can produce the waves just like how we can produce a wave of your heart rate in the hospital. Same way at JPS, at the power plant, they have these devices plotting the graphs, showing how much is being produced. So they know when there's something wrong. And then that's why so many times you guys have power cuts, because there's a dip in the graph somehow where that's not supposed to be there, which could mean some problem. And that's why they will say, all right, we could shut down the power and fix it. Or if them find out where the source is, them can just shut off the light there and then deal with it. But it comes from understanding how the AC current is produced. Do you guys have any questions?
No, sir.
All right. So that is why a graph is used to represent AC current. Again, it is reminding you of what's happening there. And so it is. Now, in this first slide I showed you, they said if the high and low voltage terminals switch locations periodically, the current will flow back and forth in the circuit. This is called AC current. The graph is shown here, the voltage versus time, and they're telling you the one cycle here. Again, when we did waves, to show you how the wave look on a graph, well, it's the same type of wave that is used for AC current. All right. And so that's how it works. All right, there is a red line that's drawn through here, which is labeled DC current. So I hope you can see that. This part here is called DC current. That's straight line. DC current is and the same graph will give you a straight line, because DC current, the direction doesn't change and the amount of current doesn't change. However, with AC current, the amount of current change. Have you ever experienced the dimming of a light?
Yes,
at
sir.
home?
Yes,
Yes.
sir.
Yeah. That's the indication that the current is not really constant. It should be.
We always call it low voltage or something.
Well, yes, and there are sometimes where it drop. So low voltage, those cars that light to dim. But that's the same thing. So this is what I was saying to you earlier now, that physics is speaking to you around you, but you have to use your sense to understand it. All right. So no, right now, guys, I can tell you the voltage. You see, because the current change, let me show you this. For AC current in Jamaica, and they might even ask it this way in the exam too. We have the frequency of the current is important. All right. Jamaica use a 50 cycle or 50 hertz cycle. US use 60 hertz. All right. Now this refers to the cycle of current that's used in Jamaica. What this mean? This is what we produce in Jamaica, 50 hertz cycle. It means that the current changes, or you could say the voltage changes direction 50 times in a second. I know if something is if 50 things, you can experience 50 changes in 1 second. Can you count 50 things in 1 second? You ever tried that yet?
No, sir. That's impossible.
You see, so you can't count it, so because you have to see it. And that is how fast the current flows, guys. Right? The current change, the dim. So basically, I know what this is saying. Let me show you something here. This is 1 second, right? Let's call this 1 second. What this is saying, is that, and remember, this is the amount of voltage, so if you should break this up, this is going to be 0.5 seconds, and here will be 0 second. Let us say this is 0.1, and then you have 0.2 there. Just for argument's sake, in 0.1 second, the voltage that you are getting is this. 0.1 more second, your voltage is this. All right, by 0.3 second. So you notice that the voltage is changing in some very small seconds. 0.1 second. What can you do in 0.1 second? You can't even blink in 0.1 second. That's fast. So the current is not steady for AC current, but it's changing. It's changing fast though. So that's why you don't see it. That's why your lights stay on. That's why everything look like it's on. But it's actually blinking very fast. All right, that's one of the things you need to understand here with AC current. All right, a lot of fast turnover happening. So that is it.
Sir, how?
Yes, go ahead.
Like it change current so fast, so like short circuit or something happened to it, sir.
Because very good question you ask. That is what comes. All right, so that is why when we design AC current appliances, there are certain things now inside of them that can manage that. All right, there are components in devices that can manage that. All right, and
yes, sir, that's true, sir.
Yes. So that is why, for example, and oh Lord, what did I do here? Yeah, that is why, for example, we have, well, if you open like a TV, you see that the TV plug into the wall. Actually the TV is blinking very fast, that's another thing. The TV has its own cycle as well. The current from the going to the TV is 50 cycle in Jamaica, 50 hertz or 50 blinks per second, if you want to call that, 50 pulse of current per second. All right. But the TV itself now designed with its own frequency. It's called a refresh rate. And that's what makes monitors expensive. The faster the monitor can refresh itself.
Yes, sir. I usually hear that in games, sir. Like, the settings.
There you go. There you go. So that's the concept there. That is due to AC current. Current is changing direction. But you have devices that can withstand that. One of the things you're going to hear about a device, in fact, let's look at some of these circuit symbols, because that's something, again, CXC will ask about. So, you will see it has been on every paper. Symbols used in circuits. Well, let's see if we can specify AC current, because we need to be able to explain what these devices do. As soon as I find something suitable. All right. So while that load, seems to be poor internet here. All right. All right. So fine. circuit or AC components in AC current AC current components. So you're going to upgrade the machine here. All right. No, come on. All right. So now AC current components. So, all right, fine. So this is the source. AC source. That's what it is. All right. Also, you have this symbol where them use. All right. They say them use it in CXC, but then what them do sometimes they even draw the symbol and ask you to state what it is. All right. We have this one. Put GEN in the middle. All right. And that would be a generator. All right. Of course, everybody should know what this is.
The switch.
Yeah, very good. All right. So that's the switch. Good. So when you're using current here, all right. There is this important thing. All right. This, and then there is also, it's actually cares, each of these components them can ask about those. So all right, hold on a sec. Let me have, yeah, this thing not responding at all.
I think the first one that over the other side is diode, sir. No, wrong.
That's wrong.
I think the other one I was talking about had a circle around it. That's why I said it was wrong.
All right. Well, we see. Let's get into the details of this one. All right. So these are components that I'm just say they will most likely ask about. This one too very common. In fact, this there are two symbols for this. So it could be. All right. I'm trying to draw it because I can't load the picture here. So.
Or sir, is it diode?
Is it? Is it diode? Well, we find out. We'll definitely find out there, January. Is that a diode? All right. These devices, I want you to know them and know the purpose of it. All right.
And the second one is a resistor. And the third one is like a bulb.
Well, yeah, hopefully I can show you. Let me show you there. All right, hold on a sec. I'm gonna go to that one. All right, guys. So the symbol here, guys. So let's label it what's 1, 2, 3, 4. All right. 4, 5, 6, and 7. All right. So yeah, I put number 4 there. Number 4, Jenna is hinting at a word that can be used to describe it. It has 2 names actually. So yes, we're gonna need to know about this device called a diode. And based on the topic sent by CXC and the exam, possible that they could ask one question about it. But I'm going to put the function of it. Diode. All right. It converts actually AC current to
DC.
Yeah.
I think the fifth one is a fuse.
But it's actually, this is a half wave DC though. So it's not, so that's it no. So it's not like if I would say AC current have that sort of wave like behavior, right? Kind of changing direction and all that sort of stuff. Putting a diode in the circuit or connecting a diode to the AC source now, it converts it to DC current, but that DC current could harm the certain devices. It's not a steady DC current. So there are other devices now that we can use now to sort of straighten out that half wave, so they can make it straight. Remember, going back to that symbol that graph I showed you, the direct current will give you a straight voltage because again, nothing is changing. Everything constant for direct current until the battery done. Because DC current is produced by batteries. Or well, you could use an AC current with with a diode, yes, but then we're gonna need other components now to make it look like this. So, and that's where the other components came in. So luckily at CXC level, they don't have a lot of components for you to know, except, well, we have a few more to add to this, but not many though when you see all the others that exist. So, but the diode converts the AC to DC. The other name for the diode is rectifier. So the diode is a rectifier, and rectifier means to correct. So you're seeing the diode can actually correct an AC current, if you want to call it that, and change it into a DC current, a half wave DC. So that's like a raw DC current where you can't use that type of current charge your phone. You'll have to have some other components. So if you should open your charger, for example, the part that plugs into the socket is AC it used, but then the other part inside the charger, that big part there, has other components that is converting into DC because your phone use DC current. So anyhow, AC current should catch your phone directly, then your phone dead. Battery blow up and basically hit that. So if your charger have a fault now where it send AC current to your phone, then that's the end of the phone. So what?
Sir, that happened with the Note 7, sir.
Well, I don't know if it happened to the. Well, I know they had a prime. No, it's different something, I think. Different. So they have other devices now, generally, that can, sort out that. But that's pretty long and short of it is that not some things use DC only, some things use AC only. Sometimes we have to convert the AC to the DC for it to be used. And then that's where these things come in now. So we have to know a little bit about that. All right. So that's where it is, guys. So wait, come in like some people drop off. Let me see something. The Chanel gone. I seen
One person left.
Yeah, the Chanel. All right. She can't manage. All right. So that's the diode. All right. Diode convert AC to DC. Bam. Half wave type of DC though. All right. So for number 5 now, guys, this thing now is like a box, a rectangle with a line drawn through it, but then because my hand's
Fuse,
shaking.
sir. It come like one fuse or one.
Actually, that's actually a fuse. And all right, guys, this is a fuse. Those so those protect devices. So it protects other devices from high current, basically. And it protects devices. Let me just. I'm probably not getting the option to erase this. Yep. I know this machine will need some memory or something. All right. So yeah, protect devices from high voltage. All right. So that's what the fuse does. All right. So bam now. So if I am connecting an AC current source to some other stuff like a fan or something, which there's a symbol for a fan, but let's probably go to that as number 8 because yeah, that's a device that let me see now. So the fan now, it really is a motor. So I going basically draw the motor. Symbol for the motor is this, you know. All right, there's a motor. So motor have a certain function. It's a circle with like 2 blades there. Yeah. All right, and of course, that's our motor. But coming back to this though later on. All right, so guys, so let's quickly go through this now. Fuse, I protect device from high voltage. Because when the current flows in a thin piece of wire in the fuse there, it's the high current actually generate heat, and then the heat melt the wire in the fuse and it break the circuit. So when the high current break the wire in the fuse, then it's not allowed to damage other stuff in there. All right, so that's how it works. All right, so if fuse coming like a bodyguard for the circuit, basically. All right, now, all right, so the next device that they could ask you about here is this number 6, and this is very common. It's a filament bulb.
Yeah, that's what I was going to say. Bulb.
Yeah. So filament bulb, it does convert the current. So converts electricity. Converts electricity or electrical current to light. All right, and then of course we have this now. This is what we call a variable resistor. All right, so that's a variable resistor. So it's just like a well, it have 2 symbols. So zigzag with an arrow there showing you. So this is like a knob that you turn. Let me show you then. Maybe show you some of the picture later on. Number 8 now would be the motor. Again, the motor have a important function. All right. All right, there you go. What's this on? All right, very good. Yeah. So here's our motor. Okay. Motor, and the motor converts so motor converts electrical current. All right, electrical current to all right, so you convert electrical current now, guys, to mechanical energy. All right, example in fans. All right, so yeah, so these are like 8 devices that relate to it. By the way, this actually regulates current. Variable resistor regulate the current. So that's like, for example, in an iron, if you guys know how the iron work, you have different levels you can set the iron depending on how hot it needs to be. And that's what a variable resistor does, just like that knob that you spin. All right, so that's basically it. All right, so that's it. So 8 devices that you're supposed to know about related to AC current, but it can also, some of them can be used for DC current too, but I'll let you know what those are. But where I focus on AC is that, well, that's what them sending AC current. So know everything related to AC current. All right, so just to recap, guys, we spoke about the definition for AC current changing its direction and flow due to the magnets that is producing the current. All right, we talk about the slip rings in the generator That's the generator is the device that's producing the AC current. The slip rings prevents what the wire from actually falling off. It keeps it in place. All right. And then now we talk about the graph of AC current, how it will look with time. Current fluctuate with time because of that rotation in the magnetic field. All right. And then what? We looked at different components using the AC current, used along with AC current. I also spoke about the fact that the AC current in Jamaica is changes direction at 50 cycle them use. So, so the current change 50 times in 1 second. In the US, it changed 60 times in 1 second. So there are some advantages to making it change faster, but that's another story. But then we ended up looking at different components we use along with AC current. And that's where we left it. All right, guys. So that's it. All right. That's just letting you know what AC current is. And then eventually now we can look at some questions now and see if any of what we just talk about is being asked. All right. Because there are so many. I've seen it so often. It's just amazing. Look at this. I mean, I didn't scroll far, but look at this. This is our first question. Just off the bat, we're seeing this question. Look at what they're asking you here. See 2 marks. Explain what is meant by the term magnetic field. Yeah. Anybody know? Anybody remember? I did mention it. When anybody remember, can say in them own words what a magnetic field is.
Is the attraction, sir, the force of attraction?
Force of attraction. Maybe get 1 out of 2 marks for that. It's incomplete though, certainly. On the right track though. Anybody want to help him out?
Sir, the gravitational pull, sir, acting around an object.
No, that's magnetism and gravity is 2 different things. That's not about magnetic field.
Sir, the force of attraction. Probably you could write the force of attraction.
The force part is right.
Around.
Well, Shanta is using gravitational field you're talking about there. That's not magnetic field. So, combining probably to another definition would probably get you somewhere. But all right, let's simplify it for you guys. Magnetic field. All right, a magnetic field is any area around a magnet where a magnetic force is experienced. All right, any region around a magnet where a magnetic force is experienced. And we're allowed to use back magnetic in this because we are being specific as to which force we're talking about. So it's really a region around a magnet where a force is experienced. So you'll still get the marks right, but I specify that the magnetic force is what it's going to be experienced. All right. That's the answer they will be looking for there. All right. And what would the answer be for this one? You have 2-bar magnet sketch a field pattern. What we expect to happen with 2 north poles facing each other? That's the question. Shanta is saying they would repel. If they would repel, yeah. So yeah, definitely. Always remember that magnetic field lines go from north to south. All right, and they said to them say sketch field pattern. Field pattern mean north is always seeking after south. So the arrow is going to leave from the north to the south. And however, what's going to happen here is that because the north is focusing on the south, it doesn't have any time to be attracting here. It's actually leaving a space between them, so there will be repulsion. All right, so you could draw it this way. They definitely repel. All right, so that's the type of thing they will ask you. Of course, you know that north and south would attract, so definitely going to have something happening there. All right, it's from north to south. There's the attraction as well, and of course, north still going to attract to south there, and so this magnet would be in between that, and that's what we're going to draw them in. All right, so that's it. All right, guys. So I'm gonna say just going, just seeing that type of question, just know so them can ask something like that. Because magnetism is on the list too, I think. So I think magnetism is on that list, Let's go back. As you wouldn't ask, yeah, magnetic forces. So it's a big deal, guys. We have to know these things. Definitely have to know these things. So that's just a little taste of the questions I could follow, guys. All right. So you guys have any question? All right. No. All right. So we have all right. So that is it, guys. So you realize that in the one class we speak about alternating current, and we're touching, it still covers some of magnetic forces there. And we mentioned motors. So all of these topics will be related. We just need to find questions that draw them together now and see if we can understand them. All right. So as we say, guys, if you don't have any more questions, then it's just a matter of you guys taking up your book and taking the thing seriously. All right. And stop being distracted. All right, let me see something. The AC current. No, probably just, did I send this? I don't think I sent this in the group. Never sent it at all. Nope. So I forgot to send this then. All right. I'm going to try and send this in the group. All right. Wait, General, come out. There, all right. So that will cover magnetic forces. All right. Bam. Let's find something else, guys. All right. Well, even this is supposed to send to you because we did do this before. Magnetism to electricity. That's the progression. All right. Yeah, so is part one. All right, there it is. That's one. All right. All right, and there's more. Oh yeah, and of course the AC alternating current generator. Copy this. AC current. AC generator. All right. Then there was the definition for AC current. AC current definition. All right. And then of course there was the AC current components. All right. Wait, January. All right. Dwayne,
Yes, sir.
you had asked me about resistance, right?
Yes, sir.
Okay. Just to confirm, guys. And I wanted to save it for class because I want everybody to benefit from it. Dwayne had asked me a question about resistance. All right. Just remember that resistance is the opposition, or it's basically restricting the flow of current in a circuit. It's just the restriction to the flow of current. So we could write that here so that you could remember that restriction or opposition.
A flow.
Yeah. Or opposition. And all right. Yeah, there you go. Restriction or opposition to the flow of charge. All right. So to the flow of current. And this by Ohm's law, really. So yeah, and when we talk about resistance now, we have to mention Ohm's law. That's we will talk about that some other time. Ohm's law will I really believe strongly it will come up in this question. If not Ohm's law, it's by itself, but the formula that's actually tells you what current is in relation to voltage and resistance. So Ohm's law basically say that what voltage and current, in fact, they are directly proportional. But then when you divide the voltage by the current, you get resistance. So that's pretty much what Ohm's law is trying to state here. Resistance is measured in ohms, by the way. So use that symbol. Current is measured in ampere, voltage measured in volts. So Ohm's law, or some books will have it as V equals IR. So yeah. All right. So resistance was actually, it's a ratio of voltage to current. All right. So how much? All right. So it's like a case like this. It come in like say, like if you like the more you press your gas in the car, the faster you pedal the bicycle is, the faster the wheel should turn. But you know that's might not be the case depending on what is probably in the bicycle or what gear the bicycle is in. So for those of you who ride bicycle, doing a ride bicycle?
No, sir.
Oh, hush. Anybody can ride bicycle, that is Shantai, Giovanni?
Yes, sir. I can ride bicycle, but I don't ride it anymore, sir.
Don't ride anymore. How about you, Amari and Kayla? And Michaela?
No, sir.
No ride bicycle? Whoa.
No,
Sir,
sir.
when I was smaller.
When you were smaller. Who say when you were smaller? Michaela?
Shantai.
Shantai? Oh, okay. But you're still small, Shantai, so how come? All right.
Sir, I'm growing it.
You're growing. Okay. All right. We all grow. I guess you could put it that way. All right. But fine. So if I ride bicycle, so that's not a good analogy to use. But then I don't know which other way to put it, but it's directly proportional. Like, you figure that the harder you throw something, like a stone, is the far it should go. But that might not always be the case.
Sir, I think everybody should know how a bicycle operates still, sir.
Oh, Well, okay. Well, just saying, the faster you pedal is supposed to be the faster the bicycle go, but then that's not always the case. You know, that's where resistance come in, because sometimes they can change the gear of the bicycle, or something is wrong with the chain in the bicycle, cause it not to really deliver the energy that you put into the pedal to the wheel. Same thing with the current here. You're sending a lot of voltage to something, and you're not getting a lot of current flowing. No, that can happen with you actually, because if you get a lot of voltage, in fact, let me show you this. And that this is why if you were to almost flatline, like a knockout or something, or you faint, and then all right, fine, you're not responding. So them get the stuff, you know, not coming to me now, but they're trying.
Defibrillator or something like that, sir.
Yeah. So that device there, you say going to send a voltage to your body, right? But it's gonna be a large enough voltage, but not too much so that a lot of current flow. Because remember, your body can't manage more than like 1 amp of current, sustain. So it have to be a big enough voltage to cause you to respond, but not too big to shock you and kill you. They find that sweet spot to revive you. All right. So that's how it is. The reason for that is that the resistance, your resistance is really high. And one of the reasons why your resistance is high is to prevent a lot of current from flowing through you. So that's where voltage and current would apply there. I mean, so that's how it works. So remember I said that you are actually producing current with your brain and so it's a small amount of current. But then I guess if you're a very powerful person mentally, you might be producing more current than normal. Maybe. Don't know if we're going to reach a stage in our lifetime where them can amplify that current and make you get very telekinetic, start move things with your mind. Possible. But then that's one of the things they use to measure people brain wave activity, which is current. So, but then,
Sir, is it true that
yeah.
our brain can power like a small bulb or something? No, remember.
Maybe. I'm not sure. I don't know personally if any study to support the same what you just say. But is it likely? Well, as I say, you'd have to amplify the current coming from the brain. So that's the only way I see it. Is that you're going to get some wireless amplifier where you put it on your head, and then whatever current your brain is producing, it amplify it on the outside to something. Almost like how the wireless charger work for some phones, like the Samsung Galaxy 9. I don't know if 8 have it. I know Google Pixel have it. But anybody have wireless charger for their phone? No?
No, sir.
Sir, my mother have it on her S9, sir.
S9, yeah. All right. So yeah, this is the time you're living in. You
So
can
I
get
think it's from S6 up or S7.
it will be 8. You can't 7. Remember I said 7 was a bomb.
Yes, sir. I think 7 have it, sir.
But
Did
7
you
was
say
a bomb. How if you dip on 7? 7 was a bomb. The 7 and over the phone will blow up.
Go
And
up
them have to call it back.
No, that was Note 7, I think, sir. Note 7.
Why? Anyway, anything named Samsung 7 still stay far from it. But then that's how it is. I'm saying that's where we are. The one thing that can protect you against a high current is the resistance. It's something that all materials have. Voltage is a force, and then you have to resist a force, because anyhow you allow voltage to get its way, sometimes it can cause a lot of current to flow and damage stuff. That happens when you get struck by lightning, for example. You can't resist the amount of voltage where the lightning having, and that's why it won't kill you. All right, you're talking about millions of volts there. Crazy. So your body can't resist that. And then too much current reach your body, you're dead. You can't manage that. There's no your brain, shut down there. For your brain shut down, that's it. So
Yes, sir.
yeah.
But sir, how does life support work, sir? Like, how does it keep your body alive, sir?
Well, that's good. Life support. So that's a case where your vitals are so low that it's then basically what them call it brain dead. You're in that stage
Yes, sir.
where
Brain dead, sir.
you're in that stage where you can't revive beyond reviving. That's every time I think about that thing, I remember some episode of Grey's Anatomy where really very emotional, but um, but that brain dead situation and it's as we say, your activity of your body gets so low that it is just virtually impossible. People can still get up though miraculous them say revive, but then it's a case where probably 8 out of every 10 times a person reach that stage, then pull the plug on them before them wake up. But then bear in mind that if you went and be on life support, it going cost. It going cost to keep you there, and people money where live a spend on it, and sometimes they must say why too much and they must call the plug, call it, pull the plug, they must call it, so you want hopefully you want to see a person come up. You can only wait so much, well, so long and no longer, because it going cost you every day. What it cost you like 100,000 a day.
Yes,
You know,
sir. Yes.
if your parent, you're close to your sibling, you go really want to do it, but you just can't do it because you don't stay like that. Even if you have insurance to the tune of tens of millions of dollars or $100 million, they will call it,
Yes, sir.
they more call it because you can money well, not say money is wasting, money is being spent, somebody have to pay, so it is. Yeah, some people say when them last wish, because if them know they more reach at a stage, them say, yo, look here, if me reach at a stage, just pull it plug, because people stay like that, just pull it. Then tell them loved ones, the doctor say, yo, if you reach a stage, just call it. Because some people don't really want to be a burden to others. But then what if them reach that stage and they didn't get to see or anything before? And it's a person close to you, I go on and keep them. You see why you need physics to become a doctor now. Physics is very crucial here. It helps you with making certain decisions with people's life, especially at that critical stage. The only thing the doctor can use for save a person at that stage is the vitals, is the readings from all of these graphs, and so where these devices are being these devices generate some graphs where you read and understand how it works and so on. Yeah, what voltage to set that the machines to that. In fact, that part of medicine is actually being called medical physics. So that field, we're a very high paying field actually, where as a medical physicist you go in and you make sure the equipment them up to standard, and you do your little checks them before it's them up to date, and know say all right, the readings are accurate. If it's giving trouble, you know how to fix it. So that's medical physics there. Very good career to go into. Just contemplating switching over to that. But we see how the future set. But definitely it's a good field where you can use your physics to save people's life. That's where it is. All right, guys. So any questions?
No, sir.
No, sir.
All right, guys. So as we say, I hope you guys learned something tonight, and you really need to learn something because exam is very near. And so hope you can just revise the notes, especially the ones that sent in the group. And I know there's something I forgot to send. I'm gonna send that question which we started to work. Let me see if I can find that somewhere here. Yeah, there it is. All right. That's like TS of the CXE questions that will follow those topics. Yeah, I'm just going to send the first part. As the other part asks about transformer. That's another big thing too as well. Another big thing. Transformers. It's not on the topics, but when we talk about electricity and magnetism, definitely the transformer. All right. So this is a sample question on magnetic fields. All right, so all right, and then we say as soon as we find them, we're not really, not hold back. Anytime we see them, we just work them. That's the stage we reach now. All right, sample question on magnetic field CSEC. That's in the group as we speak. And let's see. Let's see a thumbs up there. All right, so seeing all the material that you're supposed to have, guys. Nobody has any excuse. The topic on the screen. The topic same on the screen every night. We do something every night related to it. Videos are uploaded for class in case you miss something. Everything is there. All right. So stick with it, guys. All right. So and as we said, no activity in the group is it's not encouraging at all, because the last time something was said. See there? 5th. What? No, 15th. Today is the 26th. That's 11 days ago. Interesting. And I was the one who communicated because there was an error, a question I did. And so I corrected it then on the 15th. Yeah, so guys, I need to step it up, man, because I don't know what you guys up to. It's like you're just laid back. Physics, you can't too laid back. If you're laid back, just about probably get a 3. Can't lay back with physics. People are push. Remember, it's a competition, guys. Competition against the best and the brightest in the Caribbean. Stars in from Campion, Arden, Immaculate, places we have reputation. Not that them better than anybody else, but they just have a way to get the results. So at least more than other schools. So that's a competition for you guys. So if they do well, you have to work harder to do well, because it's the grade is a curve thing, so push the bar high. So have to make up your mind to push the bar high as well. But I've been saying
I
this,
think
yeah.
what you were talking about, like the current and thing, was that electromagnetism, like that's a further part of magnetism?
Well, we didn't specifically talk about electromagnetism, but I think one of the things I sent in the group, I think it is the second picture I sent, is talking about electromagnetism, but another class I deal with that specifically. All right. Just remember, say magnetism produce electricity, but also electricity can produce the you could say produce back the magnetism. Because it can. So we're gonna show you how that work out, and then we take it from there. All right, guys. So so that's it. I mean, been at it for quite a while here, but let me see, 7 persons stayed till the end, so that's good. Started out with 11, so all right, guys. Enjoy the rest of your night and stay safe. All right, and I'll see you guys on which day is it now? On Thursday, right? I'll see you guys on Thursday.
Yes, sir. Sir, about chemistry, sir.
Mm-hmm.
We're going to talk to you about a lab, sir. Like, we did about 9 labs, right, sir?
Yeah.
So and for the implementation, that would make the 10 chemistry lab for both physics and chemistry like in
Oh, yeah, okay. Yeah, man. So as we say, you can implement it for, but if you implement a physics one, you don't have to implement the chemistry one.
Sir, I thought if that the case, sir, I think you gave us 11 physics labs, sir.
Mm.
I think you gave
So
us
yeah,
11.
so as we say, if you're implementing the lab for physics, then you don't have to implement the one for chemistry. So yeah, that not so much for you. The physics one will be easier to implement though. So all right.
Yes, sir.
All right, then. So, all right, guys. So that's it. See you guys on Thursday.